Hi, my name is Max. I'm going to present on behalf of Team 8. We developed SPARC.RL, which is a reinforcement learning pipeline which should make medical device control easy. What motivated our work? Closed-loop control of medical devices can improve therapeutic efficacy of, for example, neuromodulation. Control algorithms are typically developed based on in silico dynamical system models obtained from experimental and clinical data as available on the SPARC platform. This requires robust controllers which guarantee safety performance, and therefore reinforcement learning algorithms are gaining rising attention. However, unfortunately, reinforcement learning requires expert knowledge and has a very steep learning curve, and therefore it's still underused in a biomedical field. SPARC.RL should solve those issues. It has the goal to combine the best number of biomedical data available on SPARC and the computational platform of SPARC in an easy-to-use tool for engineers without background reinforcement learning. For the codeathon, we chose one specific use case, which would be vagus nerve stimulation for cardiovascular applications. We developed a closed-loop vagus nerve stimulation controller using the SPARC.RL pipeline and SPARC that allows to treat elevated resting heart rates. We developed a local standalone tool to load and pre-process a time series SPARC dataset on cardiac effects of vagus nerve stimulation in behaving pigs and train a surrogate model on that. We also used a synthetic dataset generated by a model of the acute cardiac effects of vagus nerve stimulation available on SPARC and trained another surrogate model. We then chose the second surrogate model and employed the SPARC.RL pipeline on SPARC to train a reinforcement learning controller to lower the heart rate to different levels that can be specified by the user. We then evaluated the control on the surrogate model. What you can see here is a standalone client that we developed. You can pick here available time series data from the SPARC platform. We can view the dataset description here, and also we produce a suggestion on how to use the dataset in reinforcement learning using a large language model. Once you pick the dataset, you can download it to your hard disk. Next step, you can select the file from the dataset and pre-process it. You can visualize the pre-processed data, and if you are happy with the pre-processed data, you can move to the next step, which would be to design a deep neural network architecture to train your surrogate model. You can also specify your training parameters, such as the optimizer, the learning rate, or the selected batch size. And you can visualize the model architecture you generated. And once you're happy with it, you can run your training. Let's move on to the SPARC.RL pipeline on SPARC. This is a fully integrated reinforcement learning pipeline. You can upload input data to train your surrogate model using the SPARC.RL train surrogate model node. This can be either data generated through the standalone client that we have shown you before, or really any data generated by computational models. Once you have trained your surrogate model, you can move on to reinforcement learning training. You can upload a configuration file to parameterize your reinforcement learning training using the SPARC.RL train agent node. And once you have trained your reinforcement learning agent, you can evaluate it on the surrogate model. Let's move on to some results. What you can see here is the heart rate response to vagus nerve stimulation at a certain stimulation intensity. The blue line here is the ground truth data. The orange line is the prediction of the surrogate model, and you can see that the surrogate model captures the system dynamics very well. Here you can see the reinforcement learning agent training in terms of loss over training iterations. So we had 30,000 training iterations. You see a very nice convergence of all the losses over the iterations, suggesting that we found a really well-trained controller. We then evaluated this trained controller in a heart rate tracking task over 1,000 seconds, in which we varied the set point heart rate every 50 seconds, and the controller was able to really track very well the different set points. Would like to give a big shout out to the SPARC Codeathon mentors, especially the ITRS team. If you're interested in the project or have any questions, just shoot either me or John a message by mail.